Hello all, welcome to this channel CFD Baba. Here we simulate CFD cases using ANSYS Workbench. Today we will simulate flow over a car. It comes under external aerodynamics. The flow over any object is called external aerodynamics problem. In today's video, we are going to simulate flow over a simple car and try to see how the case is set up and how the post-processing is done. So first, we need a geometry of a car. I have downloaded a car geometry from grabcat.com. You can find the geometry in the link below, and you can download it and try to solve this case. First, I need to import my geometry. To do that, I will right click on geometry and select the import geometry option. Click on browse, select the car file. My file is in .stp format. Click on open. This will load the geometry file into geometry module. Right click on geometry and click on edit geometry in design modeler. Make sure that you do not open the geometry in space claim. Once the geometry has been imported, click on Generate. The geometry will be visible. This is a simple car geometry, which has been simplified for CFD purposes. You can see that the car is a solid object. Make sure that your geometry is closed from all the sides. Open geometry will result in errors. To simulate flow over a car, we first need to create an enclosure. To create the enclosure, click on Tools and click on Enclosure. Here, we need to specify the dimensions of our enclosure. Type the following dimension numbers. 3, 3. In the positive Z direction, we will have 3. In the negative X direction, we will have 3. In the negative Y direction, that is the base of the car, we will select 1, and in the negative Z direction, that is the wake region of the car, we will select 4 meters. Click on Generate. This will create an enclosure which has been designed so that the inlet length is shorter than the outlet length. So the outlet length behind the car is bigger by 1 meter. This helps us to accurately predict the flow region behind the car. That is called wake region. Now we have our solid car and the modeling of a wind tunnel. To simulate flow around the car, we only need to model the air that is there around the car. So we have already done that in format of an enclosure. But the solid part of the car is still present inside the fluid domain. We need to subtract it from our fluid domain. To subtract the solid domain of car from our fluid domain, we will use Boolean subtract operation. Go in Create, click on Boolean. In the operation type, select Subtract. Now we have to select the target and tool bodies. Target body means the body from which we are subtracting our object. Tool body is the body which we want to subtract. So select car for our tool bodies. Click on Apply. Click on Generate. Now you can see that the car body has been deleted from our fluid domain. Here we have to assign the property as fluid. So make sure that the property of this new enclosure is set to fluid. So we have successfully modeled the air that is there around the car. If you want to see inside the domain, we can use the section plane option. We can cut our geometry into half by using the section plane option. As you can see, the car that was the solid part has been deleted from our fluid domain. And now we are only left with the air which is there around the car. In fluid dynamics, we mostly solve for the fluids. Here, we do not need to consider the solid part that is the car. We will only consider the air that is the fluid domain. So, close the section plane and you can see that we have our enclosure ready. But if you observe our geometry, you can see that our geometry is symmetric around YZ plane. So if you have got a symmetric geometry, then you can simulate only for half of the domain. So to create half domain, we will use the symmetry option. Select the solid, click on Tools, and click on Symmetry. Now the software will ask us around which plane do you want the geometry to be split into symmetric parts. So the plane about which we want our geometry to be split is the YZ plane. So select YZ plane, click on Apply, and then click on Generate. The software will remove half of the geometry and you can see that we have the symmetric half of our geometry. We can simulate this part and apply symmetric boundary condition to get the full results. This is how we modify our geometry and create a fluid domain in form of enclosure using Design Modeler. Next, we will go for meshing of this geometry. Close the Design Modeler tab and open Meshing tab. Once the geometry has been imported into the Meshing tab, click on Mesh, click on Quality, and select High for smoothing. In this problem, we will create the mesh using default settings of ANSYS Fluent. So click on Generate Mesh. You can see that we have small edges and faces in our geometry. So fine mesh will be generated on those faces. Once the mesh has been finished, you can see that the default settings of the mesh have been able to capture the small features that were there in our geometry. So, fine mesh has been created to capture the small features, and large mesh elements have been created for rest of the domain. We will use this mesh to simulate flow around this car. To simulate the flow, we need to select the boundaries. Click on the inlet face, right-click and select Create Named Selection. Give the name as Inlet. Click on OK. Select the walls of the enclosure. You can press shortcut key N to open the Selection Name tab. Type in the name as walls. Next, we will select the outlet face. Press N. Type in outlet. Press OK. Now, we need to specify the symmetric face around which our geometry is symmetric. Click on the symmetry face, press N, and name the face as symmetry. Make sure that you name it as symmetry so that ANSYS can identify this face as symmetric boundary condition. Now we have to select our car. To select the car, press on wireframe mode. Then select the box select tool. Now you can draw a box around your car and the car faces will be selected. Make sure that you have turned on the face selection filter. Once the car faces have been selected, press N and name these faces as car. Click OK. Now you can check that we have all our boundaries which can be used in ANSYS Fluent by assigning the proper boundary conditions. If you go in Workbench, you will see that the mesh needs to be updated. So before closing the mesh module, we'll right-click on mesh and click on update. This will make sure that the mesh has been updated in the Workbench area. Once the mesh translation to Fluent is successful, you can close your meshing module. Next, we will solve this mesh in the setup. Right-click on setup, click on open. Here we'll select double precision and I will use parallel computing. You can select the number of cores in the processes. I have 4 cores, so I will put in 4. Press OK. This will import our mesh into the Fluent tab. Once the mesh has been imported, you can assign the boundary conditions. If you want to view the mesh of the car alone, then you can click on Display, select only the car and click on Display. This will show you the mesh for your car. To view whole geometry, select rest of the faces and click on display. Now we'll assign boundary conditions to all the faces. First, we need to select our turbulence model. So go in models, double click on viscous laminar, and you will get an option to select all the different turbulence models. Here we will use K-epsilon 2 equation model. Click on OK. Next, we will assign boundary conditions. Make sure in materials that the fluid selected is air, because we are simulating flow of air over our car. Next, we will go in boundary conditions. In boundary conditions, we have to select inlet. Make sure the type is velocity inlet. Click on edit. Here, we will assign velocity of 20 meters per second, which is an average speed with which a car travels. Click on OK. Select the outlet and make sure the type is pressure outlet. Select on symmetry and make sure the type is symmetry. This will tell the software that our geometry is symmetric around this face. Next, we will select the method. We will use coupled method to solve our solution. We will use second order append scheme for more accurate solution. Next, we want to initialize our solution. To initialize the solution, we will use standard initialization from inlet. Click on initialize. Once the initialization has been done, we are ready to run the calculation. We will run our calculation up to 100 iterations. But the solution may converge before 100 iterations. To make sure that doesn't happen, go in monitors and then double click on residual. Here, we can switch off the convergence criteria for our convergence. So tick off all the convergence criteria for all our equations. Click on OK. Now we are ready to run our calculation. Double click on Run Calculation and click on Calculate. Here you can see that the residual graph has been plotted and it will run up to 100 iterations. We want our residual values to be as low as possible. Order of 10 raised to minus 3 is mostly preferred in most of the CFD simulations. So we will wait till all the 100 iterations have been completed. So the iterations have been completed. You will get calculation complete message. Click on OK. Make sure that the residual graph is heading in the downward direction. If the residual graph values are going in the upward direction, then you need to recheck all the setup in your CFD case. Now, we will try to visualize the results. For visualization of results, we will open the post processing tool, that is CFD Post. Right click on results and click on open. Once the results are loaded in CFD Post, we can visualize the flow over the car. To see the flow over car, we need to create a plane. Click on location and then click on plane. Click on OK. Now we are asked the plane which we want to create. The symmetry plane in our case is YZ plane. So I will select the YZ plane. Click on apply. Here we will get our plane. Now we can visualize the results. First, let's visualize the contour. Click on contour button. Click on OK. Now we are asked the location of contour. We want to see the contour on plane 1. Let's look at the velocity contour. Select variable as velocity and range as local. Click on apply. Here you can see that the velocity profile has been plotted. Go in render. Switch off the lighting option. Click on apply. Now we need to smoothen our contour points. So select 110 number of contours. Click on apply. So now you can see that the contour is more smooth. So this is the flow of velocity around car. If you want to select user specified values, you can select the maximum range as 20 meters per second, which was our inlet velocity. Click on apply. Now you can see that the velocity at inlet, that is 20 meters per second, is being shown correctly. And here at the flow separation point, there is stagnation of velocity, and here the velocity is almost equal to 0. So this is a correct representation of the actual scenario. However, the values are just for demonstration purposes. These values cannot be used in experimental results. To change the legend type, click on Default Legend View, then go in Appearance and click on Fixed. Click on Apply, and you can see that the numbers in the legend are more easy to read. This is how we visualize the contour. Now let's visualize the vectors. To visualize the vectors, click on the vector button, click on OK. Now we can hide our contour. In the vectors, we need to specify the location. We will select the location as plane 1. Click on apply. Here you can see that the vectors of velocity have been plotted on the YZ plane. So we can see that the air is coming in through the inlet, striking the car, the flow separation is taking place, and then the flow is going out through the outlet. So make sure that the direction of velocity is correct by using the vectors. Now we can also visualize the streamlines. So let's hide the vectors. To visualize the streamlines, click on Streamline button. Click on OK. It asks us from where we want our streamlines to start. We want our streamlines to start from the inlet, and we want the direction of our streamlines forward and backward. Click on Apply. This will plot the streamlines in whole fluid domain. If we increase the number of points, we can see the flow that is taking place in the fluid domain. But if we want to visualize the flow only on the YZ plane, then click on YZ plane, that is plane 1. So we will select Start from plane 1. Click on Apply. Now you can see that the streamlines are more easy to visualize, and we can see how the streamlines have been formed. So in the wake region, that is behind the car, we can see eddies forming. These eddies are formed when the car moves forward. The interesting property of fluid is that it tries to stick to the surface of anything that it can find. So the fluid behind the car tries to stick to the surface behind the car. And when the car moves forward, the air which is trying to stick to the surface is also pulled forward. And in this type of phenomenon, we get the formation of eddies. So this is how we can visualize the flow that is going over our car. We can also select the range which we want. Right now the range is from 0 to 36. I will go in the color and click on local range. Click on Apply. And if we want user specified range, then we can enter the values that we want. I will plot the range from 0 to 20. Click on Apply. Now you can see that the air is coming in at 20 meters per second. But as it impacts the car, the velocity around the car and behind the car is decreasing. So this is how we can visualize the streamline flow around our car. We can also use the animation option to animate the flow particles. To create an animation, click on Animation button. Then we have to animate the streamline 1. So click on Streamline 1. Set the speed as slow. And then you can click the play button. Here you will be able to visualize how the fluid particles are coming in through the inlet and going out through the outlet. Click on Stop button. The particles were very large. To select the size of the particles, click on Options. Here you can find the symbol size. Reduce it to half. I will select 0.5. Click on OK. Now we can visualize the streamlines flow again, but this time we'll increase the speed a little bit. Click on Play Animation. Now you can see the size of the fluid particles is reduced, and it will look much more better when we will view it in the form of an animation. Click on Stop button. You can also save this animation file by clicking on Save Movie. So this is how we can visualize the flow of air around any object. In our video, we have selected the car as our object. This car can be replaced by any object. That can be an aeroplane or a building or a wind turbine or any type of object that you want to study. In short, you can select any object around which you want to visualize the flow of fluid and use the same procedure to solve any kind of CFD problems. So this is all for today. Hope you have learned something new and enjoyed this video. If you have liked this video, share it with your fellow CFD colleagues and do not forget to like, share and subscribe to this YouTube channel. See you in the next video. Bye bye till then.